Hello. Hello. Start. We started looking at Wi-Fi, MAC layer, and we saw that at physical layer we already have difference as compared to the wired Ethernet, and then at the MAC layer, do we need to have a difference or not? And then we looked at the medium, and as compared to when you have all the laptops and desktop around the hub switch or Ethernet, everybody can hear each other. So the medium that works for the MAC layer on that model is all the nodes can hear each other. And I showed you one example in wireless where you might have a scenario where the nodes are hidden from each other, which means not everybody can hear each other. Okay. So if an example of this is, although this is connected networks, that means you can have a path. The A and C cannot directly hear each other, and with this, your MAC layer will break. Because the traditional MAC layer, which we say CSMA CA, this is the Ethernet MAC layer. That does not work out here. Okay. So we have to investigate and come up with a new MAC layer. And today we will see what that new MAC layer is. Before we look at the MAC layer, one old technology that's there, right, for 802.11b. So what is the current technology that we use for multiplexing on 802.11? Do you remember what is the multiplexing? OFDM, right? These days we use OFDM. But previously, just before that, there was a version of CDMA that was used for 11B, not 11B. So you know what frequency division is, you know what time division is. What is the code division? So CDMA is something where you can use two transmitters can transmit data at the same time at the same frequency. So that means I and you can talk at the same time, and you and I can also use the same frequency, but still the receiver can recover my signal separately and your signal separately. So what is an advantage of this technology over TDMA and FDMA is, right, you have better utilization of time and frequency. Okay. But now how do you get back signal? If you just think about it, you and me talking at the same time, at the same frequency, how do you recover the signal? Right? Is there some magic? Because traditionally what we know is two people cannot talk to each other. Or at least they should be, right, your frequency should be, you should be some another animal and another person should be another animal. Right? So their frequencies are different. And then you get both signals. So how do you get both the signals together? So I will give you an example. This is called CDMA, And again, I'm giving an analogy, but this is just an analogy for you to understand these things. Right? It is not exactly how it works. But the way it's working is, I have a secret share between myself and the receiver, and you will have your own secret share between you and the receiver. By the way, secret I'm just saying as a key. That is not, doesn't have to be really secret, but we can keep it secret. And then whenever I transmit, I encode my signal by applying that secret key. And then when you transmit your signal, you encode your data using that key. And now both the data will go together. At the receiver, he knows both the secrets. One between share between myself and the receiver, and another between you and the receiver. And he will apply the reverse of that to the signal. So he will decode it using two different keys, and he will recover back both the data. Okay. So it's, we are looking at a dimension. So there is a time dimension, there is a frequency dimension, and there is another dimension. So if you see, this is time, this is frequency. Right? So there is another dimension which is the code. Right. Right. So if they overlap, right, synchronously on top of each other, right, the way it works out is at the level, on the dimension of coding, right, they are still separate. They're separate. Right, so that's what happens. So if you think as in terms of time, you know how, if you're separated in time, what will happen, right? On the frequency dimension also, you know if they are separated in frequency, they have some spacing. So that's the spacing. And if you have it on frequency, you know what will happen, right? I'm saying, just consider, just take my word for it, right? That there is another dimension to this world, which is code. Right? And if our encodings are separated, sufficiently separated, then even if they, like, in time and frequency they are overlapping, but in the code dimension you can separate them out. And I will give you one example of this. This is a very simple example, right? But in the practice we use more complicated ways of doing it. So the way it works out, right? This, if you be a little patient, you will understand how it is going on. So you use a unique code assigned to each user. So every user has to get a unique code. That's the first condition. Right? If you share the code, it will not work. Okay. All users share same frequency. Right? They use the same frequency to transmit. But each user has its own chipping sequence, which is the function of the code. I will show you what chipping sequence is. But they have separate codes. Now, how you encode signal is you take your original data and you apply, I'm just saying multiplication, it's not exact. In this example, it is multiplication, but it could be another function also. And you apply this encoding on the data, and that's your encoded signal. And the decoding is just the reverse of this. Right? So if this is multiplication, you divide it. Right? That's the reverse of multiplication. And then you get back the data. Okay? Now, so this, let me just show you. The magic happens here. So let's say this is your data bit 1. And you want to save my data as 1 bit. Then what? This is my code. Right? So if you see the frequency of this chipping sequence or the code is more than the data. Okay? What you do is you multiply these two and you get this one. So this is multiplied by 1, right? The multiplication will be same as the encoding or chipping sequence. Okay. Then for the second data bit, my second database is -1, right? It's binary. And then I apply this sequence again. This is my code, the same code as here, right? But because this was -1, this gets inverted and you get this one, right? And you keep on doing it. You have more data bits like this, 1 -1, 1 1 -1, right? You keep doing it, right? And this is what you will transmit. Right? At the receiving end, this is just for one sender. I have right now only one sender. You take the same data as in whatever was transmitted. Right? So in slot 0, you get this thing. Right? And then right, here it is still multiplied. Right? This is the function I use for decoding also. Right? So this is slot 0, and this is exactly same as this one. I multiply it, and then I find out an average of this. So right now my data is not this one. For the receiver, whatever the input is, it's this sequence. Right? So there are multiple of chipping. And this thing is also the same. Right? So you multiply these two. Maybe you can give it a try. Just multiply these two and find out what is the signal you get. Okay. Just try it out. 1, 1, 1. There's 1 here. There's 1 here. All ones. Right? So what it is doing is adding up all these ones and it is dividing by number of chips in that. 1, 2, 3, 4, 8. Right? So 8 divided by 8 is 1. Right? So what you recover is this one. Okay. So the best way to explain this is you give it a try. Right? Have you understood this part? The one about the red line. That's easy. Like you see zeros, you see +1 and -1 as your 2 bits. Binaries including. You multiply it with this chipping sequence. And chipping sequence is 1, 1, 1, -1, 1, -1, -1, minus. Right? So it gets multiplied with the data, and what you recover now, the way you recover is you just multiply it with the same encoding. Right? So if you multiply, what do you get? This bit by bit. It's all 1. Right? With all ones, if you add up, it is 8, and you divide it by 8, right, you get 1. And that's how I show it here 1. Questions on this? Okay, code was given by Roland. It's magic. Right? I just gave you the code. Right? You can give me data, you can't give me code. I will give you the code. Okay. So you can give me the data, this is the code, right? Okay, what will be the next thing? Can you do it for the next one? I'm not showing it. Right? So this is your slot 1. That's what you get in slot 1 at the receiver. Right? You apply the same rules. Right? Is this okay? Right. So what is the data that you receive at the receiver finally after decoding? Same data as the transmitter, right? Okay, so that is one sender, one receiver. Okay, that's easy. There is no multiplexing happening right now so far. Okay. The multiplexing kicks in when I have 2 senders. Right. So this is my 1 and -1, and for the another sender, I have 1 and 1. Right? But if you now look at its secret or its code or its chipping sequence, it is different from this one. Now I'm saying it is 1, -1, 1, 1, 1, -1, 1, 1. Okay. Now can you do this thing and tell me if this is correct? You have to do the same way of encoding. Right? That means multiplication of this. And this is slot 0 and this is slot 1. Right? So slot 0 is overlapping of this sender with this sender. Right? So when you send it together in the time domain, this signal will get added because it is going at the same time. Take a movement, see, it's just very Yes. When we are in slot 1, this one, this is -1 into -1. That's +1. Right? And this is +1 and +1. This is 1. So 1 plus 1, 2. So let's take this example. The last one. This is 1 into -1. This is -1. This is 1 into 1 is +1. 0. Right? So I just check 2 bits. You can do the rest of it. Right? And so this is what it comes out. Right? So now we have a legal interference happening in time domain. Right? On this axis, in this dimension, the two senders are actually interfering with each other. They are transmitting at the same time, synchronously. Signals will overlap, right? And that's how we get it. So this is happening at almost the frequency physically. See, I'm talking about signals. I will very quickly tell you about physical here and then we'll go to math. Right? So what you are talking about is the magnet, which is this one is still physical here. Right? We don't see multiple players and all that. Right now, this is the bits. Right? So this is physical here. Okay, so far so good. This is what you get here, right? And you now apply the code. So this is the code for first sender, right? And you apply it on this signal, which is different, right? Exactly the same way. What do you get? Right? So the example that I showed you in the previous slide, you applied the coding again at the receiver, but this signal was different. Now what I have here is this is added in another sender, and so at the receiver end I don't know this, right? I don't know whether the signal is added or not. I just apply the coding again. What do I get? Right. So you can try for one slot. Just verify. That's what you get. Anybody has arrived at a different data other than this one? It's the same way. So let's do it. This is 0 into 1, 0. Right? This is -2, this is into 1. Right? So this will be -2. So you can write 0 -2. Right? This is 0, so it is 0. This is 2, and this is -1, so this is -2. Right? And so on. And you add up all these two together and you again divide by 8. What do you get? -1, okay? And you will get +1 here, right? So what is the magic that happened here is, even if I took a signal which is added with another transmitter and applied the code of the first sender, I recovered sender 1's data, right? And if you apply now this code on that same data, right, magically you will receive this one and 1. Right? You can give it a try. That's something I might also do for the homework. Right? But if you are quick enough to do it, you just apply this one and this one together. You do the same summation divided by m, which is it. You will receive back 1 and 1. Right? So you can exactly get back what sender 1, sender 2 transmitted. That's not, is it a negative code? So this is 1 and this is 1. Right? It's not exactly inversion. These two codes are not exactly inversion. Right. Right. So what we call it is not negative, right? What you need is orthogonal codes, right? So negative means they will cancel each other. Orthogonal means they will not affect each other. So these two codes in coding theory, we say these are orthogonal codes. That means you can in parallel use them and they will not interfere with each other. Right? So that was the magic that happened. Right? And the person who developed this came up with a company called Qualcomm. Right? And then he made a lot of money. Right? This was all patented. He got this idea first of having different codes, right? And he gave us a method, just like you all know RSA, right? RSA encryption and decryption. There is a public key and private key, right? And that pair is like married together, right? You use this public key and then you have to use that private, and so on, right? Same thing with this codes also. If you get, so I just presented you two codes. If I have 8 orthogonal codes, right, that means I can give it to 8 different transmitter, and they can transmit data at the same time. And the receiver, when you apply these codes, right, you can recover back all the signals for 8 transmitters. Right? So that's the coding technique that was used, and because of this coding technique, right, the whole world changed. You can transmit at the right. So sender and receiver, they know their codings. So in this example, the receiver doesn't know whether one is transmitting or both of them are transmitting. It just applies the encoding, decoding technique. Right? So it wants to decode first sender data, it will apply. That's it. So it will apply all codes. Let me give you a very simple answer. It will apply all codes to recover back every sender. Together as in one, so one at a time. Right? You say, so for the receiver, it's like this. He gets one stream, which is this one, right? And what comes out of the decoder is this stream and this stream. And this is sender 1, this is sender 2. Okay, so let me take it back. The way it will work out, right? Maybe I was wrong there when I said that. For this particular scenario, the way it happens is at the sender and the receiver, they know how will be multiplied the channel. How many transmitters will be there, how many receivers, one receiver, and how many transmitters will be there, right? And you get back the signal. Now, another question is if you don't know, like you are asking right now. If you don't know how many senders are there, so I need to verify that, right? But if everybody is transmitting and all the data gets combined and you receive like the decoder, you apply one code at a time and you get back everybody's data. You separate it. Just like a multi-mode does. So slot is in time, like the first beat that you get, that is your first slot. Right? So everybody's first slot is together. Slot 0. Then you give and so on. Because when the decoder spits out the bits, right? Slot 0 for everybody, and slot 1 for everybody, and slot 2 and so on. Keep on doing. Right, so that I was right. I know. So let me take it back. Let's simplify the things. Right? I would say right now is all the transmitters are doing at the same time. Everybody is transmitting all the senders. Right? I'm not saying that if one does not have data, what we need. Then I need to verify it. I have to do the computation and see. Right? But the thing is, if everybody transmits, everybody has data to transmit, then you can recover every individual's data separately if you apply their individual codes at the decoder. How is the? Right. Just like we do in the time domain. What do we do in time domain? I tell this sender that you transmit in first slot and you transmit in the second slot. So that's a shared knowledge between transmitter and receiver beforehand, offline. How does the receiver know that this is the exact code which I have to apply? Right. So there is some central authority which tells the transmitter and the receiver. This is your, it tells sender this is the code, and it tells the receiver also this is the code, just like private key and public key. Right? There is a central authority that will tell the sender and the receiver. These are the codes. Right? So this is yes. Right. So let's assume for now, as I was saying, everybody wants to send data. Right. In that case, this will work out. Right? I will verify when only one or some partially they want to send data. What happened? Right? I said in that movement that even partially it will work out. Right? But I will verify that. Okay, but for now, everybody wants to send data. Then you can recover the data. Okay. So as you see, this is a big step, right? So far you had only known that at a time one person can talk or on a frequency one person can speak, right? But what I showed you today is at the same time in the same frequency multiple people can talk. And this is just an example of two senders because we want to simplify things with our computation. But the CDMA that we use in mobile networks, right? One cell phone tower gives out these codes to multiple people. Right? And all the phones can now talk at the same time, at the same frequency, and the tower, cell phone tower, can recover every individual signal. Right? So Reliance had this CDMA technology, but now everything is CDMA. Right? With 3G and onwards, and everybody uses CDMA. Right? That's the reason why they use it. And this was used for .11b, but it turns out OFDM is a better technology than CDMA. Right? So there's a big competition why it is better, but like overall it gives more reliable and robustness. And the spectral efficiency, there is something called spectral efficiency of OFDM is better than this one. So we use OFDM with 11.g on this. Right? So 802.11g is OFDM. And most of the latest LTE and everything they use OFDM. Okay. So now this is physical layer. I just very quickly looked at the physical layer, CDMA, and now we look at the MAC layer. Okay. So this is, by the way, also called as direct sequence spread spectrum, DSSS. Because you take one bit and you spread it out across chipping sequence. So that's why this is also called DSS. Right? So that is what 802.11b uses. Right? And with G, with today's standards, we use OFDM, which you already see. Okay. Questions now? So after this, we will look at the MAC layer. Right. So we are done with the physical layer. There is nothing more at the physical layer. Okay. So typically, any 802.11 network in the enterprise or at home looks like this. You have access point, you have clients. There's another access point. There are another set of clients connected to that access point. And all of these access points are connected to one hub, switch or router, which you see in the network stores, and then they are connected to the internet. Right? And that's the big network. Now we all know how network and how routing happens in the internet, so we are not going to look at that. We only focus here, here, and here. Okay. So this is called a basic service set. Whenever you see a cell, so there is one access point on top near the projector. Right? There could be more in the back. There is one on there. So we have three. So we have three access points. Each one is 4. So there are 4 access points, and they are giving out one basic service set around each other. Right? And they are overlapping here. As you can see, they are overlapping here. Okay. So this is how the network is set up. And you see there is one cable going there outside. That's this cable. And this is going to the first switch, which is there near the elevator. And from elevator, it is going to the server room. From there, it is connected to the internet. Okay. Based on the signal strength, or does the access point decide? So, okay, let me. So the answer is a little complicated, right? How it happens, right? What happens is, so let's say there are 2 of these access points only. Let's simplify the situation. There are 2 of these which are overlapping, and you are in the middle. If you are on this side of the access points, you can't see the other one, right? That's easy. The complex scenario is AP1, AP2, and you are the client here, right? What should happen? What is your guess? Right. But see, if these 2 access points, they are advertising something we say SSID, which is students N for you. Okay. Now this students N is, this one also advertises, this one also advertises. Right? So although the basic service sets are different, right, the SSIDs are the same. That's now is very different from what I'm explaining. Okay. Now within the same SSID, your device will connect to the one which is having more signal strength, and it will associate itself with that. Right? If you don't have a key for this access point for some reason, let's say you are at home and your neighbor has one access point and you have it, and you don't know the password for the other neighbor's key, right? Then even though you get a better signal strength there, you have to use this one, your own one. Okay, so it's not just the signal strength, right? Other factors also, security and so on, also will determine. Yes. Right. So it will try to associate with the, but it has to know the password. If it knows all the passwords, so if your machine knows passwords of all the networks in the world, right, it will always go to the best one. This is the model of our network. Right? Right? So as we were talking about this association, it scans channels listening for the beacon frames containing SSID and the MAC address. Right? Selects an AP associate with, mostly with this better signal strength. It will perform an authentication, that is that password, WPA2 and so on. You should know that password. Right? And after all these steps are fine, then it will run DHCP. And there will be some DHCP protocol which will get you an IP. Right? So this is how this thing works out. Okay, 802.11. So again, 802.11, it's actually an entire, not only course but area in itself. Right? So it will be very hard for me to tell you everything. So I will tell you few things. Just remember that this is very big or vast topic. Okay. So now the whole point of today's lecture is this CSMA protocol. How do we modify CSMA? Do we throw out the CSMA and start from scratch and come up with a new protocol? Or can we modify CSMA, which is we know in the Ethernet works out, and we use it? So can anybody remind me how CSMA CD works? If you remember the CSMA CD protocol that you studied. Anybody? Right, very good. Right. So first thing, let's start from the basic, the beginning. Carrier sense. Right? The first thing any client does, it senses if the carrier is there. That means if anybody is transmitting. If anybody is transmitting on the medium, you will not transmit at that. Okay, so that's the carrier sense. Right? And the next one is collision detection, which means if you transmit, and you can also hear at the same time on the wired Ethernet, because the bits go around the switch and come back to you, and you see this, there is a collision because what you receive is not what you transmitted, right? It is a garbage. You see there is a collision, and you stop the transmission, right? You then send another garbage signal so that everybody knows there is a collision, and then you back off. That means you wait for some random amount of time. There is a random back off, and then you repeat the protocol. Okay. If next time also you see a collision, what do? You increase the back off exponentially. Right? So everybody will start backing off with a bigger delay. Hope is one guy will win, and the line will start losing. So that's the protocol. In wireless, we cannot have collision detection. Why cannot we have collision detection? You know the reason. In wireless, we don't have a capability to detect there is a collision. I gave out the reason last time. There is one big reason.
When was the same as not against collision happens, then we utilize that value was not the same as what he said, and therefore he sent out that garbage signal. In wireless, there are already too many communicating.
It's not about too many communicating. Even two guys are there, you can't detect. There is one reason here, but the another reason is, as I said in the last class, when you are sending or transmitting, you cannot receive in wireless, right? So that means if I am transmitting the data, and if there is a collision that's happening, it's actively getting collided, I can't listen to that. I have to finish the transmission. I might get back result right after my transmission is over and there is a multipath and the signal bounces and comes back, and I see okay, there is a collision. That's there, right? We can't do that. In wired, we can do that. Yeah, so the reason is if you open up a switch, it's like this. That's your PC1, that's your PC2, right? You are sending this cable here, and then there is another cable, and this guy is repeating the data here, right? So it's wires basically. You can put two wires together. It's on which on the one wire you transmit, on the other one you receive, and you can do that. In wireless, you cannot do that. You have just one antenna. It is actually being used for transmission, right? And then you cannot receive at that frequency. Okay. So that means, right? We cannot take this protocol. So wired Ethernet protocol, CSMA CA, as we know, we can't use it, right? So what we do is, instead of collision detection, if you know from your, if you cannot detect deadlocks. We try to avoid deadlocks. Right? So what we do is we have another protocol, CSMA, we can detect set carrier, but we use something called collision avoidance. So instead of detecting collisions, we'll avoid collisions. Right? And that's the protocol I will show you today. It might seem that the protocol is easy, right? But even after this, take out some time and read it again. It's not so easy protocol. It handles a lot of complicated scenarios. So I will just give you out the protocol and then we will slowly look at it, how it is working. This is the sender, this is receiver. Sender senses that the channel is idle for some amount of time, which we say DRFS. Right? So that's where the first protocol actually changes itself. Right? You sense the channel, and if it is empty, you do not transmit immediately. That's one difference. That means I hear nobody is saying anything, I do not start talking immediately. I wait for some amount of time, which is DRFS, right? And then only I say something. Now, why do you do that? Right now, nobody is saying I should immediately say, but I wait for some time. Anybody knows the reason?
Somebody says then there will be a
Right. Right. So there is significant propagation in wireless. Right? It takes time for the signal to propagate. So by the time the sender at the another corner starts saying something, right, it will take some time for the signal to come at me or arrive at my location. Right? So DRFS will make sure that within that entire service cell, that circle that I showed you or the cell that I showed you, right, it's the function of the diameter of that circle. Right? There is this access point and there is this circle. Right? So that's the diameter. If I make sure that even if this guy transmits, it will take some amount of time for signal to arrive, right? And it is always less than DRFS. Then I'm sure that if I wait for DRFS, nobody is saying right now, and nobody's data is also in the transmission, right? So I can transmit it.
transmitters use the same protocol at the same time.
Right, so that will happen, but at the beginning, let's avoid one collision where you say something, right, just before I started saying, right? So that will not happen. Okay? So if the channel is idle for DRFS amount of time, then you transmit. Right. So we take the maximum value possible. So that's why Wi-Fi has some range, right? Every Wi-Fi, it's hard-coded, but it comes with it. So that's why if you take Wi-Fi and put it on top of buildings and you try to communicate with each other, that protocol does not work correctly because the calculation of DRFS is such that it will apply for a room or a corridor. Right? They usually take some distance and they work it out. Right? So that's why you cannot use Wi-Fi to send data from Earth to Moon. Right? The DRFS is actually just gone for a toss. Okay, so that's why you can. So they say this is home router, this is enterprise router, and so on. So once that is fixed, what we do is if the sense channel is busy. So before going to the collision, if the channel is busy, what do you do? Right. So the way it works out is not only of course you should not transmit. And that's the basic thing. First thing you should do. You should not transmit. But not only that, you start a random back of timer, right, which is counting downwards while the timer is idle and transmit when the timer expires. Right, so you have a countdown now. And you keep on counting down till that timer reaches 0, and if it reaches 0, right, you will transmit. And this is actually a very simple statement. The protocol is really complicated than this one. So I will tell you what is the complication. But the timer should come down to 0 and then you transmit. And then for every data, let's assume that this transmission was fine, there is no collision. Then you will receive back an acknowledgement. So you send data, I have an animation here. So there is DRFS, you send the whole data, and after some time, the receivers will send you back an acknowledgement. If the transmitter receives an acknowledgement, that means the data was transmitted fine. And of course, the acknowledgement also goes fine. So you don't need to transmit. If the acknowledgement is not there, what do you do? That means with very high probability, there is a collision. I send the data, I did not get back an act. That means my data lost somewhere. Assuming they are not out of coverage. After they are out of coverage, right, they have to give up. There's nothing you can do. Right, so we'll come back to that. But after the data went fine, you get back act. You don't get back act, that means there was a collision. That means multiple people are trying to access the channel. So you should increase your random backoff, and that's exponentially getting. You increase it now. And you will again start counting downwards. Right? And then when you get channel empty, you will send it. There is another collision, you will get again there is exponential increase in the backoff. And you will keep off backing off till a maximum limit. You don't want to go to infinity. Right? And after that, you say when the network is gone, it's back. Your Wi-Fi card gives up. Okay. Now, one question is why SIFS, why not immediately? So everybody knows these values. The device is born with these values. Right? It's hard-coded. They know the right first time. Even though they are different devices, that's the protocol standard. IEEE 802.11. Right? So Wi-Fi card has to follow this protocol. That means it has to know what is DIFS, what is SIFS. Everybody knows these values. And everybody follows the protocol. Nobody is malicious in this. You say acknowledgement is slowly coming back. Right. So that's why I also said about something about DRPs. How large can it be? Right. So we assume that this value is such that even if the receiver and the transmitter are maximally apart, right, that is fine. So it will not be a case that you are fast and the other one is slow or very far and you don't hear back. Now, one question is, so I will ask you one question after this one, but before that, why do you wait for some time? First thing is you have to get back the whole data, right? You have to do all the CRC checks and everything, right? Verify the data is correct and it is for you and all that, right? That's why you have to look at the header and see, okay, it is me whom the data was sent to, so I should send that. So there is some processing delay that gets involved in this. You cannot instantaneously send something back. When you first verify the frame was not damaged, it was meant for you and everything, and then you say, so that there is some time given to the receiver to do that process. Right. So either this could collide or this could collide. This guy, sender doesn't know this. It cannot differentiate between these. It will just say there is a collision somewhere, right? And I have to slow down. If many people are trying to access. It doesn't matter whether the data gets collided or not. But another thing is, I'm saying that data will. So, what should be the relation between DIFS and SIFS? Which one is greater? Yes. So, these are two numeric values, right? These are constants. Now, what is the relation? Is this equal? Certainly, it's not equal, right? Because I would have just write DIFS. Right? So, it is either this or this. Why?
Because if it is smaller, then there is a possibility that before SRS finishes, it will start sending.
Right. So other sender who is looking to get channel will see, okay, it's empty for a long amount of time. I should look at a DIF. So it is there, right? Nobody is transmitting for DIF this amount of time. So I should immediately send it. right? And nobody will then, the receiver will not get a chance or an opportunity to send back an ad. Some sender will immediately step in and send data, right? So that's the relationship. The BIFS is more than SIFS. Right? It has to be like this. Yes.
So the BIFS is equal to the one download time plus.
Yeah. So it's around that one, right? So if you now do the all calculation, right? Like I said, the diameter, how much time does it take, and all that. You compute all that, and like, you can derive it. It has to be certainly more than that. So these are the values which are hard-coded in your wireless Ethernet card. They always follow it. You can these days even change these values, right? But then your communication might break unless you know what you are doing. Right? It's not a good idea to change these values. So I think I have another slide and then I can come back. Okay, now what happens is, so one thing I missed out here, which I have posted in the backpack, and it's, I think it's also there in this book. Right? It is not as simple as this one. What happens is when the timer is, you are counting down the timer, right? Somebody transmits. What should we do? So there are two senders now. Right? Sender 1, sender 2. Right? At this point, right, you have this random backoff, and right, this is your random backoff. Right? We are counting down the time. Right? And it will reach 0 here and you will transmit it. Right? At this will also probably have its own random backoff counter. Right? It is also counting down. This, for him, it expires here. Or it goes down to 0 and it transmits now. What should the sender 1 do? Right? So the question is, if I am counting down and I am also sensing the channel, right? Of course I will not jump in before the timer expires. But before my timer expires, I see another communication on the channel. What do you think should I do? Should I just ignore it and okay, I just keep counting down?
Because even after this random level, we're going to check.
Okay, so let me so one thing you said is you increase the backoff. What did you say? Right. So in a way, you have also increased it. Right? Her increase is bigger. Right? You just exponentially go to a big value. Yours is smaller. What is it? You just don't ignore it. Right? If somebody is saying something, right? So what do I do here? If he transmits just here.
You want to sense it after the random backup end. You again going to sense that, and you again going to wait for the DIFS and then you again start.
Okay.
Then also you can detect the collision. If there is again a collision, then you can go for a bigger random backup.
Okay, so you are saying that till this point I don't listen anything, right? I just shut down totally. I come down to the 0 value, then I again sense the channel and I take some action. So let's assume there is no hidden terminal. Because that's, I think it's question, but it's a different question. Right? Okay. So let me just give you how 802.11 does, right? And then you compare how it is done. The 802.11 standard says if you ever hear anything while you are counting down, you stop your time. You don't waste your time. Why? See, the whole point of backing off is let other transmit. So let me not let other transmit. Let me back off so that the channel gets less busy, and then I will make an attempt. Right? If you see that somebody else is transmitting, that means you see, okay, so the standard says let him finish. I will now stall my time. at that instant. Right? I will not waste my timer. Let him fully finish whatever he wants to send. And then let there be a DIFS amount of time and nobody is transmitting. And then again I will resume my timer. So there is a pause in the timer here. At this instant you pause it. Right? And this instant, once the transmission is over, right, you resume. You resume your counter now, and then you count it back. Again, if you hear somebody talking, you pause it. So that means you are not putting the additional penalty of what you are saying. It's just increase exponentially, again increase exponentially. That way you will very quickly hit the maximum. Right? So instead of doing that, let him finish. Right? And once he is finished, channel is idle, you resume your time. And you count. Right? So you will wait for certainly for this amount of time and more. And that more is, it's a linear function of number of frames transmitted by other people. Right? You only have exponentiality in one thing. Right? You don't go for exponential and bigger exponential. Exponential plus some linear thing, it depends on how many other centers are there. Okay? So you don't change your timer value, you just pause it and resume it. Okay. The way it works out is, if ever you start your random back of timer, right, and you start counting down, you still keep on sensing the channel. If by the time your counter timer reaches 0, you have fully done the counting and nobody has attempted any transmission, that means the channel is idle for the whole time. Now you are free to transmit. You will do the transmission. Right? That's the good scenario. Another scenario, if ever you hear within that timer that you're counting down, anybody transmitting, right? You pause your timer. You don't keep the clock running, you pause it. And you keep sensing the channel. The other person is done with the transmission, it receives the acknowledgement. And for DIFS amount of time after this, right, there is no other transmission. Then you resume your timer. So you should see, while your timer is running, the channel should be idle all the time. That is how you can derive. That's the derivation. Okay.
You said when I pause my timer, when I sense somebody else setting something, and I resume my timer after somebody has received its acknowledgement, final acknowledgement, plus the DIFS timer. So why to resume timer then why should not I just start sending? Because now the channel is free.
No. So it's your, so the sender's obligation is to run down the timer. Right? It has increased the timer to some value exponentially. Right? So it has to run it down.
But the sender has just sensed that he was the last sender.
So if, let me give you another example. If 5 people are running down the timer, one guy is done, everybody pauses it. If 6th one sends something, if he's done, all 5 can jump in. Right? It will be, right? It will be. Everybody is running the timer. Right? All of them pause. One guy transmits. Whoever is other guy is transmitting. The 6th guy. Right? His transmission is over. DIFS time. Nobody transmit. All 5 of them jump in. Right? So it's your obligation to run down the timer. So in simple words, it just let every communication go through. It's not really looking at whether it's data or acknowledgement. It's just looking whether the carrier is busy or idle. No. See, everybody gets the 5 people I talked about, right? You break the so there's a competition between 5 of these, right? And you order them by way of their timer value. Everybody has selected it randomly, right? So that means very high probability each one of this has got a different value. So you can order them. So whichever has got was lucky and having the least value, right, will get a first chance. Yes.
So and the other when the other also start sending, then you have to again wait for
Yes.
that data and the acknowledgement.
Right.
So it becomes a good thing in place one sender is always
Right. So I'm saying that it's not going to infinite, right? You might have to wait small amount of time. You might have to wait more amount of time.
all depends on the
But
number of senders.
there is a fairness. No, there is perfect fairness. And the fairness is if you have 5 of these, let's say there are 5 people in the network, right? Everybody will, let's say, in the worst case, has got some random number, right? The channel is, right, it's jammed, it's congested, right? So you will have 5 random values. And 5 random values, now you will not change these random values, right? Every sender is committed to its own random value. So you just order it. Whichever, so R1 will know if this is the relation, right? So the one with the least will get away first. And then the second one, and then the third one, and then the fifth one. So you can order the random values, and that's the order, right? So there is a fairness involved in this. Unless you are timer, you always select the maximum one, at which nobody will do. Okay, so this is how the protocol works out, right? So as you see now, at no point in time I say we detect a collision. You cannot detect a collision. The only way is you try to avoid it as much as possible, right? By doing this collision avoidance technique, right? You have these random backoffs. You pause the timer, you let everybody finish, and then you transfer. No. So it will transmit and it is done with the transmission. Right. So there, see, typically what happens is you have lots, right? Your data is getting bought, right? It's backlogged. Right? Now you'll push all of your data. Once you get the channel, you just push all the data. And then typically you are done. Of course, there is a scenario when you again come back immediately after that. That's rare. Right? And then at that point, what happens? You have to wait, right? Other people are waiting for random. So you might win at that. But then if there is a collision, you will have again a big random. But typically what happens is you get the channel, you push all of your data, and you are empty.
Next we assume the case that the sender has to send 8.90.
Then it's gone.
The least
Right.
backup, least random backup time. Then we keep on sending and block here.
Right. So that's where the access point comes in. Right. So access point can finally see, okay, this client is sending too much data. I should stop it. Right. So but right now we are not looking at access point. This is fully distributed. There is no central authority. Okay. Other questions? So I have also posted a PDF. Right. You go through the slides, you go through the book, but also look at that PDF, which will tell you more all the details about how it happens. Okay. So one last thing about this, and then we stop today. Right. So the hidden terminal problem is not dealt out. Right. We still have the question of hidden terminals. So the way hidden terminal works out actually is really easy as compared to this protocol. The way hidden terminal works is you have a request to send and clear to send message. Right. So the node who has got you actually told me the protocol last time. The one who wants to send sends RTS, request to send. Right? And the receiving end, if it receives multiple RTS, all collides, right? They are wasted. Then they again try, and if you receive one RTS, you send clear to send, which everybody will overhear, right? And then only one node who received that CTS will transmit. Okay? And that's how the protocol works. And this is how we deal with hidden node terminals. So that's simple. RTS and CTS. You request first and then only you transmit. And these frames will also again will follow on that DIFS and SIFS business. Right? They are not just independent frames. So let me just show you an animation. RTS, CTS, collision. Right? You again get the back off, and then A's back off timer is less. So A can send it. And AP receives it, so it sends CTS, CTS. Both of them will receive it because they are in the range of access point. And then A will send the data. Access point sends an acknowledgement. which B also gets it because it's within the range, and now it knows that it can attempt to send this RTS again. Right? So it will send down.
I'm okay with this.
So this is sent in the air. Everybody in that range will receive. Right? A will be happy because its data got through, and B will consider this to be a message saying now I can send an RTS. Right?
So RTF is sent after
You can assume that for now. Right? I have to look at exact values, but these are of the order of SIFs. Right? But this data, as you know, right, this is for SDFs and SIFs. So there will be SIFs separation after the data.
Data, suppose A wants to send a lot of data, then all the data is sent in the same time.
Yes. So A says that in the RTS itself that I want to send let's say 1 megabyte of data, or in amount of time it says I need 1 millisecond, entire 1 millisecond to transmit, right? So AP will see okay, he needs to reserve this thing for 1 millisecond. I allow it or disallow it. If allows it, it can send the data for that whole duration.
That means then A sent by the receiver is saying that A has finished.
A has finished. Now he doesn't want to send anything more. If he wants to send, he has to again do the RTS business. No. It may or may not. See, if it's received internally, we don't need RTS.
So
If B can hear A, you do not need RTS and CTS. The MAC protocol will just work out. BIFS.
There might be same data. We are also receiving the same data because it is in the air and in the range. They might
Security is handled by the layer above, by the encryption. Right? At the header level, you just see the sender, receiver, and you see just a bit data, which you may understand or may not understand. So in wireless, I actually see all your data, right? But it is encrypted, that's why I cannot make a sense of it. Yes. No. So what happens is after this collision, that's when the random thing comes up, right? And it is counting it down, like in a way. Now it sees this RTS, and then it doesn't see the RTS, it sees the CTS, right? So it knows now for this much amount of time I cannot get the channel.
after taking the app of it,
Hmm.
we know that it can send the updates now, and
Right.
maybe it can take the CDs.
Yes.
But it's random because it's larger than
Right, so that's the question about that fairness, right? What will happen? But as I said, I said that random, right, it will be some fixed value.
random backup has to be on.
Right. Right, so that will also work. Or the other protocol where, right, you just immediately attempt to send RTS. That will also work in this particular case. Right? Because we are not talking about data.
After this FFA is sent by the receiver, it is received by all of them, including A.
So any message that AP sends is guaranteed to be received by everyone. You cannot say the same thing about any other message.
Actually, the hidden terminal problem ends after this. After they can be hidden terminal problem only once they are sending. Because after this, everyone knows that there is a A in this vicinity.
No, they know there is A, but they can never know that A will transfer.
The normal problem will still remain, but the hidden terminal problem will end, isn't it?
Right. So with this protocol, you will not get collisions. The data will not collide. If you follow this protocol, you will collisions, so the data is not there. Question?
So basically, after receiving it, participant A has to send all after receiving it, we sending it about wait for some time.
No, so B would say RTS again.
So immediately after that, if it is completed its long time, it's still
Right. So that I am not committing right now. Right? In the worst case scenario, the maximum amount of time you write down the time. Right? And then you do.
the RTS, when there is a of the RTS, then you decide that it's random backup.
Right. See, if your RTS goes and you get back CTS, you don't need random backups.
You get a collision, you put your own random value. Let's say A has a random about 10 and B has a random about 12. So in those 2 seconds, if B does not get back the CTS of A,
So once there is a collision, they both does a random backup, and then hopefully they are well separated in time. The backups are not exactly same. If they are same, then again they will collide.
if the backups are different,
Different. That means once RTS will come to the AP and then you will get back
but
CTS.
before that APS comes, the random backup B gets finished. Before the CTS from the AP comes to B, B's random backup gets finished, and B
And same as RTS getting collided again. So that's what I said. The separation between two things should be more than RTS and CTS, both propagation.
So the random backup difference should be more than the time taken
For RTS and CTS to receive. Okay, so this is the MAC protocol. Right? This is the MAC protocol that 802.11 uses. Okay, so there is an animation also. You can go through the animation. It's in the book, right? You see the link. You can find. Otherwise, I have put up a slides also. Questions? Doubts?
So, like in this case, you said that once it detects that once it detects that okay, sender whose transmission is done, it will again start the sender. I understand. I mean, computer that let's say still 10 seconds are left. So now it will count. It will again start its timer for 10 seconds.
No, no.
After 10
Okay.
back to the end.
Right.
So again, there's a possibility that another sender will send. So why does it go on? Because there's always a possibility that another sender can send it and again it's back on again start.
The way it works out is everybody selects some random value, and that range from which you select a random value, right? There is a separation between the values that you select, right? And initially the ranges are smaller, and if you collide like this again and again, then only they increase, right? So at the beginning when they're small, right? The hope is what random value I select and what you select is there is less than or greater than relation, and whoever has the less than will send all of its data, right? So it will be happy after that, and he's not going to attempt immediately, and then your random backups will expire immediately after my transmission. And you don't select such a big value that I transmit and then have another need to send data, and then I send that, and that keeps on happening. So it's not on that range; it's on a smaller range. Okay. Yeah.
after detecting the CTS of A, it still keeps on getting the keeps on receiving the channel.
Who?
The CTS of A does that CTS contain information that how much time A is
Right.
running.
Right. So it's not doesn't have to. Right. It says how much time it is A is going to use this channel.
But if it takes the time and starts to counter and finishes, and
So this in this slides I'm not really committed to the timer one. Right? Only where like I'm saying that it has to just differ for that much amount of time. Right? So you can think of it as a pause and resume thing.
that is during that different amount of time,
Right.
is we still listening to the channel. Because if
No, it doesn't have to listen to the channel. It knows for sure A is going to transmit. It can listen, but see, AP has already committed that I'm giving channel to A for this much amount of time. Right? And then it cannot do anything. It's either in the control of A or access point to cancel this reservation. And B is not going to do anything.
we does not need to do anything with A, you can connect with every time AP also. That's all.
That's a separate question, right? And when you change your AP, then you don't even need this business now. This is within one AP, right? If you change your AP, then why waste your time sending RTS here?
During that different phase, they cannot go to a different AP, send data and come back and then back.
If you find another AP, you just go and talk to that another AP, right? Where you will send more data. I come back here where there is already congestion. So let's stop here.